So stereoisomers, new terminology here. It's a type of isomer. So we rarely just say isomers because we want to be more specific. Stereoisomers are compounds that have the same atom connectivity but a different arrangement of atoms in space. So if you describe this compound, for example, you'd have a carbon-carbon double bond. This carbon's bonded to a chlorine and a hydrogen. This carbon is also bonded to a chlorine and a hydrogen. This carbon's bonded to a hydrogen and a chlorine. This bonded to a hydrogen and a chlorine. Okay, so we have the same connectivity, but we have a different orientation in space. So for this one, this chlorine is up and that chlorine is down. So they are stereoisomers of each other. And likewise, when we have a ring, this bromine here is up. On the top side of the ring, chlorine is down. So we could call that trans, right? That would be trans. This would also be trans. So we have this one, the bromine and the chlorine are on opposite sides of the ring, bromine, chlorine on the same side of the ring. So of course, we already introduced this terminology. This would be trans. This is cis. This is trans. And this is cis. So those are stereoisomers of each other. Same molecular formula. Same connectivity. That means all of the atoms are bonded in the same way to the same atoms. We have a different arrangement of atoms in space. Another example of this is starch and cellulose. And starch and cellulose are made up of repeating glucose units. This is a glucose that's in a ring. There's a glucose, there's a glucose, there's a glucose. And we have completely different properties. The only difference between starch and starch and cellulose is, see the orientation of this bond right here? See how that's axial in starch? Everything else, I promise you, is exactly the same. Right here, however, that orientation, that's equatorial. And that one little tiny difference makes a completely different physical properties. So here we have glucose. Let's label this glucose. Glucose, and likewise glucose and glucose. And again, the only difference here, axial and equatorial. And it turns out that that one little bond there makes these compounds have completely different physical properties. So cellulose basically ends up being a flat molecule. You get sheets of it. And then they hydrogen bond with each other. So there's very little hydrogen bonding in the exterior of the cellulose. So it's water insoluble, even though we have the exact number of carbons and oxygens here. Starch, on the other hand, because of the orientation of this bond, it makes the molecule go into a helix. And so in that helix, we have the hydrogen bonding with water all along that helix and kind of towards the interior of that. Your book has a really good picture of it, but anyway, so that completely changes it. So that starch, the helix, water soluble. Cellulose, which gives rigidity to trees, to the trunks of trees. Tree trunks and plant stems. Water insoluble. We'll talk more about both of these compounds when we get into 51C. It's actually the last chapter where we talk about carbohydrates. But we certainly know that the trees don't dissolve when it rains. So we know that cellulose is not water soluble. So pretty amazing.